Bismillahirrahmanirrahim. Assalamu alaikum and good morning. I am Dr. Muhammad Nomani Kabir from the Faculty of Computing. This is our work on the mathematical model of lung functionality using pressure signal for volume control ventilation. As we know that mechanical ventilation is extremely important to support the life in the intensive care unit for the patient having lung malfunction. Lung malfunction can happen due to the different reason. For example, the diseases like pneumonia or the current COVID-19 situation. So therefore, the mechanical ventilation plays a crucial role in critical care. There are a number of models using single compartment to describe the lung model, representing lung elastance and the airway resistance. The model sometimes incorporates the lung volume and the airflow as well as the PEEP. PEEP is important because it reduces the alveoli collapse by exerting extra pressure at the end of expiration. This process reduces the risk of lung injury. Therefore, the PEEP is important, and furthermore, there is another importance of PEEP, which is to reduce the workload of breathing. Hence, titrating PEEP is essential for mechanical ventilation to optimize the lung characteristics. Most of the previous works use the pressure and the flow signals as input data in order to validate the single compartment model. In this study, we developed a single compartment model supporting the volume control ventilation by using only one kind of signal, which is the pressure signal. And the aim of this model is to compute the lung volume and the compliance correctly. In reality, for volume control ventilator, the lung volume should remain constant, even in the change of pressure. However, if the PEEP is added in the lung model, then the lung model output volume increases, which in turn affects the compliance. Therefore, to keep the lung volume constant, we add a negative feedback to the lung model to remove the amount of volume which increases due to the peak. We collect the pressure signal in real time during the mechanical ventilation using the one interface device which we developed by ourselves. The purpose of the interface is to collect the real-time pressure signal of the lung. We implement this model in lab view that uses just the pressure signal in order to compute the volume, airflow, and compliance. Now we describe the methodology. The lung functionality can be given by equation number 1 and is illustrated by the figure on the right hand side. In this equation, we can see that we have a number of variables, which is P, R, Q, EV, and P naught. So P is the pressure and P naught is the minimum or minimal pressure signal, which represent the PEEP, and PT, T represent the time, discrete time, P the pressure at time T, and we have R, who's the resistance, as we can see on the figure here, right hand side. Q is the flow, represented by the change of volume over time. E is the elastance, which is the inverse of the compliance. and V is the volume at time t. So if we consider Qt as the derivative of uh, the volume with respect to the time, then we can find this equation 2. And another important equation is given by number 3, which provides the lung compliance. In that we have Dt, which is the change of the volume, and PPL, which is the plateau pressure that actually represent the maximum pressure signal, and the PIP is the minimal pressure signal, which is the same as P naught. The methodology is given by the figures from number 2 to number 4. Number 2 provides us the basic component involved in the proposed model. We can see in this figure 2 on the right part is the mechanical ventilator itself, and the flow is coming from the mechanical ventilator to the analyzer that gives us the measured data of the pressure signal, volume signal, and the airflow signal. And that flows through the lung, artificial lung. Actually, that can be replaced by the actual patient lung, but we just want to test it, so therefore we just use here artificial lung. Then there is another connection from the outlet to the interface device, and interface device flows to the LabVIEW platform. So these two items are shown in figure 3 and figure 4. In figure 3, we have the interface device. In that we can see that the pressure, the signal is coming from the mechanical ventilator, and it goes to the pressure sensor. So we have a pressure sensor to sense the pressure, and that pressure is amplified, and then we convert this pressure signal, which is in the analog form, to the digital form. So analog to digital converter. So finally, we have the numerical value of the pressure signal, which goes into the LabVIEW platform. So in the LabVIEW platform, we have get the pressure signal from the interface device, and from the pressure signal, the pressure values flows to the lung model, and lung model computes the volume, and from this we can compute the differential volume with respect to time. We compute the airflow, and the volume and the pressure signal are used to compute the lung compliance as well. We check that we have a negative feedback from the volume, which is given by this figure more clearly. One can see that the part of the pressure is moving and subtracting from the PT actual inlet pressure, and then we have the PE, the modified pressure, which moves in the lung model to compute the volume over time, and also that compute the change of volume over time, which is the flow. So now this scenario is given by number 4, that we can see that the feedback is subtracted from the actual pressure coming from the ventilator. So then PT is calculated as this one, which is given by number 5. So if we put the value of number 5 into the previous equation, which is 2, then we formulate this equation. That is our model. Actually, the LabVIEW will calculate solve this model to find the volume Vt and the Qt, which is the flow, and also it will compute the compliance. This is the result which we obtained from our model. In this picture, we can see that we have actually 3 basic scenario with 400, 500, and 600 milliliter volume, but we just used here 400 milliliter volume just for the sake of simplicity. And we showed here the pressure and the volume signal over time. We also made for each scenario 2 types of experiment. One is without feedback, the other one is with feedback. So we can see that, of course, with feedback, our result is much better than that without feedback. So finally, we put all this result together in these two tables. One can see that these are the three scenarios, 1, 2, 3, and we have two types of experiment. One is no feedback, another one is with feedback. So without feedback, we get the average error as 9.28, and with feedback, we get the result as 5.14. So that means with feedback, our result is much better than the result without feedback. And this is more clear here in this scenario where we compute the lung compliance. The lung compliance value without the feedback is estimated as 16, and the average error for the case with feedback is 2. So finally, one can tell that the model with negative feedback shows better performance and acceptable accuracy as demonstrated by the experimental results. We can use this model in order to compute volume flow and compliance using pressure signal only, real-time mechanical ventilation. And we can check the ventilation performance using this model. Furthermore, this will facilitate the clinician and the apprentices to practice on and they study on the real on the lung model instead of the actual patient lung in order to avoid the injury. So thank you very much for patience. If you have any question, please write to me an email. I will be happy to answer your email. Thank you.